All right, welcome to Math 30-2. This is Unit 1, Lesson 1. And this is Introduction to Set Theory. So the first thing we're going to review is just number systems. And you've seen this in grade 9, 10, and 11. But we'll just go through a few things to do with the real number system. So the first set of numbers, which is like the smallest set of numbers here, is natural numbers. It's a group that starts at 1. It includes 1, 2, 3, 4, 5, and so on. To note, 0 is not part of this group, and it has no negative numbers. All right, so if you're thinking about the number line here, it's starting at 1, 2, and it's going up, counting numbers. Okay. The next set of numbers is the whole numbers, and that whole numbers includes the natural numbers. It has one bit of a difference, okay? Whole numbers, this group has all the natural numbers in it, plus 0. So it's one thing bigger. Well, I should have said this has... None of these numbers are decimals. They're just the counting numbers. All right, integers, very similar, but it includes all the whole numbers in it. But it also has the opposites. Now, the opposites of the whole numbers are going to be the negative numbers. Now, rational numbers, this is anything that can be expressed as a ratio of two integers. All right, so it's basically anything that can be written as a fraction. So things like half or negative 2 over 7. So you're going to get some decimal stuff. The important thing about this is that the decimals are going to end. All right, 1/2 is 0.5. Okay, if you have something like 0.2 5, that's an ending decimal. All right, now you can write that as a ratio. 0.25 is going to be 1/4. All right, so anything that can be written as a fraction, that's going to be included in the rational numbers. Natural numbers, whole numbers, integers, they're all included in rational numbers. So one thing to note here is a set is a collection of objects, things, or symbols which are clearly defined. All right, if you think about like a Lego set, you have the exact number of Lego pieces to make that set. All right, that's included for that particular Lego model. They're denoted with uppercase letters. The individual objects within a set are called elements. Elements are written inside curly brackets. So example, define the set of numbers on all of the sides of a 6-sided dice. A set must be properly defined. So there's 3 ways of doing this. Now we're going to list the elements. So the first thing is to list everything in here. So this is set D. Now, if we think about a dice, you're going to have the number 1, 2, 3, 4, 5, and 6 showing. All right, and all of these are the elements. Those are all the possibilities when you roll a dice. In some instances, it's possible to list all the elements of a set. It's impossible to list all the elements of a set. And we can define the set using some additional methods. So we can use it using words. So if we think about 1, 2, 3, 4, 5, and 6, let's go back to our number system here. Where are 1, 2, 3, 4, 5, and 6 going to be a part of? Well, they're the natural numbers. Remember, natural numbers don't include 0. So if we want to describe this same element using words, this could be the natural numbers less than or equal to 6. We're going to finish off with a set of curly brackets. We can also describe this using set builder notation. So it's a mathematical notation for describing a set by talking about the properties that it must satisfy. So the set D, we're going to be talking about X. All right, so the straight line that I'm going to put here refers to such that. So we've got the set D. The set D is equal to the elements of X such that, and here's where we're going to define stuff. X is going to be less than or equal to 6, and X is an element of the natural numbers. So we've defined all the same things, but 3 different ways. Set notation. So the number of elements in a set D is written as ND, with D in brackets. All right. Now this thing here is known as cardinality. Do you need to know that? Probably not right now. So in the above example, how many things are in the set? Well, there's 6 elements. All right. This sort of stylized E means that it's an element of. Now, if we do that same stylized E but put a slash through it, it means it's not an element of. Anytime you see an equal sign with a slash, that means not equal to. All right. So anything with a little diagonal slash in it means not. So we relate an element in a set using the symbol E. If an object X is an element of set A, we write XEA. If an object Z is not an element of it, we write Z with the E with a slash A. Example. The number 2 belongs to set D, but the number 8 does not belong to set D. To express this, we can write 2 is an element of set D, but 8 is not an element of the set. The order of listing elements in a set does not matter. For example, we could have written this, the set D is D equals 4, 3, 6, 5, 2, 1. They're just elements of it. So let's consider 2 sets. So we've got set P, which are whole numbers less than or equal to 3, and set Q, which are even whole numbers less than 10. So we got to think about the first set here, set P. Whole numbers less than or equal to 3. So if you can look back on your first page set of notes there, and the whole numbers include natural numbers with the addition of 0. So the first set here is going to be 0, 1, 2, and 3. Okay? And set Q is even whole numbers less than 10. So we also have 0, 2, 4, 6, and 8. So let's display these sets using a Venn diagram. All right, so we've got set P, we've got set Q. Now, is there any of them that are common between the 2 sets? Well, 0 is going to be the same for both, and it looks like 2 is the same for both. So if they're both included, they go in that middle section here. Now 1 and 3 are only a part of set P, and 4, 6, and 8 are part of set Q. So if you look at this big circle here, or oval, you've got 0, 1, 2, 3, which is set P. And if you look at this oval, you've got 0, 2, 4, 6, 8, which is set Q. There is this overlap, which means that it belongs to both set. So let's complete the following. How many elements are there in set P? Well, there's 4. And how many are there in set Q? There's 5. So let's write set P using set builder notation. So P, we've got X such that X is less than or equal to 3, and X is an element of the whole number system. Which of these is going to describe set Q? All right, well, let's just maybe think about what each of these is actually going to be involved. So X is less than 10, and it's a whole number system, so this is going to be all of them. All right. Q such that E is 2 multiplied by X. All right, and X is going to be between 0 and 10. So if X is between 0 and 10 and we're multiplying it each time, well, 2 times 0 is 0. 2 times 2, or 2 times 1 is 2. And then we get 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. 2 times 5 is 10. 2 times 6 is 12. 2 times 7 is 14. 2 times 8 is 16. And 2 times 9 is 18. Now, notice there's no equal sign here. Okay, so that means that 10 is not included in it. So 2 times 10 would not be an option. All right. Now we've got this set Q with elements E such that E is 2x, but x is going to be between 0 and 4. So 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. Now it is equal to, so you do get that 2 times 4. And the last one, we've got these E, where E is 2x, and where our options, our x's, are going to be 0, 1, 2, 3, 4, and 5. So it's going to be very similar to the last set, but 2 times 5 is 10. All right. So if we compare this to our last set P here, these are the ones that we want. 0, 2, 4, 6, and 8. So which one matches that? Well, it's this one here. Okay, so that is not correct, or I shouldn't say it's not correct, it just doesn't match what we had before. All right, let's do another example here. Betty is defining sets using non-negative single-digit numbers. So non-negative single-digit numbers. So that's going to be whole numbers, 0 to 9. All right, so if that's our first sort of, it's what we've been defined. So our options are between 0 and 9. All right, so let's talk about the even numbers. So the even numbers are going to be 0, 2, 4, 6, and 8. All right. The whole numbers less than 7. Well, that's going to be 0, 1, 2, 3, 4, 5, 6, 7. And odd numbers less than 7. So we've got 1, 3, and 5. 7's not included because it's not less than or equal to 7. So in set builder notations, we need to figure out how do we define something as even. All right. So we're actually going to say E such that E is equal to 2x. Anytime you multiply something by 2, it has to be even. All right. And x is going to be less than or equal to 4, because if we multiply each one of those by 2, you'll get what we need. And our last parameter here, x, is an element of the whole number system. Okay, we've got this set L, and we've got 0, 1, 2, 3, 4, 5, 6, 7. So we've got x such that x is less than 7, and x is an element of the whole number system. If you don't put this part here, you could technically have other things, 1.5, 2.5, 3.5, 6.5, anything in between the numbers. So as soon as you define it as XEW, that means that it has to be a whole number system. All right, now odd numbers. Now a trick to make any number odd is to multiply it by 2 and then add 1. Okay, it doesn't matter what number you're putting in there, you'll always get an odd number. If you just have 2x, that automatically makes any number that you substitute in for x even. All right, so if you put in 2 times 7, you get 14. All right, but if you do that additional plus 1, you are guaranteed to get an odd number. So anytime you want an odd number, start with that E 2x plus 1. Use that 2x plus 1. Now, what numbers can we substitute in for x to get 1, 3, and 5? Well, if we say x is less than or equal to 2, and x is an element of the whole number system, we have defined it. Okay? Whole numbers means that it's going to be 0, 1, 2. And if we're saying that x is equal to less than or equal to 2, that means it's defined to 0, 1, and 2. Okay, or sorry, it's limited to 0, 1, and 2. So let's display the relationship between sets E, L, and O using a Venn diagram. Okay, well, if you notice that 1, 3, and 5, okay, 1, 3, and 5 are contained in set L, right? They're the same numbers. So if we put 1, 3, and 5, that's going to be set O. Okay, I'll just use a different color here. Okay, so this is set O. All right. And if we add in 0, 2, 4, and 6, we get the other options for set L. And our last set is E. Now, is there anything that's in set E that is not in the other set? Well, the only number that's in set E that isn't in set L is the number 8. Okay. Now, there's some numbers that are, oops, I made a mistake way back up here. This 7 is not included in this because it's less than 7, not less than or equal to. All right, so if we go back to our original options, there's two numbers that have not been placed in either set, and those numbers are 7 and 9. Okay, they are part of the universal set. Okay, that was our first thing that we were dealing with, the whole numbers 0 to 9, but they weren't in a subset. They weren't in E, L, or O. So we just have to place them outside of the circles but inside the box. So the universal set is a set which contains all objects. So the universal set for this is whole numbers less than 10. And we've got the universal set is x such that x is less than 10 and x is an element of the whole number system. Okay? So that's the universal set. That was the first thing that we dealt with, the whole numbers 0 to 9. Okay? And then we had these subsets. So a subset is a set that contains some or all the elements from a previously defined set. All sets we deal with in a problem must be subsets of the universal set, and every set is a subset of itself. All right, it's pretty wordy, but in set notation, we use this symbol. It's kind of like a C to mean is a subset of, and the symbol C and a slash to mean not a subset of. So set E is a subset of the universal set U. So we say E is a subset of the set U. That means if you look back, E, this set, is contained within our overall set. 0, 2, 4, 6, and 8 are all part of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Is E a subset of L? No, it's not. So E is not a subset of L. Set O is a subset of L, which is a subset of U. So that means if you look back to this picture, O is contained within L, and L is contained within U. So how we define this, you just use additional symbols. So O is a subset of L, which is a subset of U. An empty set is a set that contains no elements. The empty set is a subset of every set. The notation for this is O with a slash through it. For example, the set of all numbers in set E is O with a slash because there's no odd numbers in set E. Provide another example of a set that's empty. So a set of integers which are both even and odd. Are there any numbers that are both even and odd at the same time? No. So it's an empty set. Set of integers greater than 10 and less than 5. Is there any number that's greater than 10 and less than 5? No. So it's an empty set. So that's lesson 1. Here's your practice problems. The answers are at the end for you.